In this video, we're going to talk about fixed points of functions. Fixed points of functions. We're going to mainly be approaching this on a very elementary level. And let me give you the definition. Suppose we have a function, say f of x. A fixed point say, let's call it p of the function is a point such that f of p is equal to p. In other words, when you put that value into the function, you get the same value back out. Now, it seems like this wouldn't have a lot of application, but later in math and more advanced math, you can use this idea to solve many problems. It can even go as far as in partial differential equations, you'll have places where you can use the fixed point method to solve problems. Here, we're going to go over the basics. So first of all, let's look at some examples. Let's take a look at this function here. Consider f of x equal to x squared minus x. Then a fixed point of this function is x equal to 2 because when we put 2 into the function, we get 2 back out. So that would be an example of a fixed point. Now, this one also has another fixed point. It looks like if you put 0 in here, you'll get 0 back out. But I'm just want to just give an example. And let me just mention that also f of 0 gives 0. Now let's consider this function here. Consider g of x, x squared plus 12 over 7. And here's another fixed point. Note that if we put 3 into our function, excuse me, getting a little bit ahead, we get 3 back out. So 3 is a fixed point. And another one, G4, 4 squared plus 12 divided by 7. And what's that going to be? 16 plus 12 is 28. And we get 4. So 4 is a fixed point. Like that. So here, these are just some examples of fixed point. The fixed points here, 3 was a fixed point, 4 is a fixed point up here, 2 is a fixed point, 0 is a fixed point. And of course, it's going to differ as the functions differ. Now we can find fixed points graphically as well. If you make a graph of your function, you can just find the places where the input and the output are the same. So here we have this function g of x equal x squared minus 2, going from -2 to 3. Actually, I've graphed a little bit beyond where we're told here. But in any case, here's the picture of the graph. And a fixed point, once again, will be any place where g of x will equal to x. And we can find this very easily if we draw a line y equal x, because that's really what we're looking for. We're looking for the places where y is equal to x. And so if we draw the line y equal x, let's say it's like this, and say this is y equal x, then any place that crosses this line, in other words, any point of our function that crosses this line y equal x is going to be a fixed point. So you can see over here, this is a fixed point, and you can just double check that here we're putting into and we're getting out to. So that's got to be a fixed point. That's at the point x equal 2 is a fixed point. And also notice it crosses the graph down here, and just double check. Here we put in -1 and get out -1. So here as well, x equal -1 is a fixed point. So that's a way graphically you can do it. Just draw the line y equal x, draw your function. Any place where your function crosses y equal x is going to be a fixed point. So how do we find points by doing calculations? How do we find fixed points? Simply set your function, set f of x equal to x, and solve for x. And it's the simplest way to do that. As I mentioned before, you can do it graphically by seeing where the function intersects. See where the graph of the function intersects y equal x. Or if you do this, which you can do then, you can set fx equal to x, then solve f of x minus x equals 0. In other words, set this equal. That's what you're looking for. You're looking for an x such that f of x equal to x. Then rearrange it to solve for this. And so let's look at some examples. Find fixed points. Of a f of x equal x squared plus 7x plus 8. So let's take a look at this one. So do what we set up here. Set your function, which is this, equal to x, then solve for x. So again, just rearrange this. We can bring this over to the other side. And that if we subtract that, that'll give us 6x plus 8 is 0. Then go ahead and solve this. You could do this several ways. Probably the easiest thing to do would be to factor this. You could use a quadratic formula if you wanted to, but factoring is going to be a little bit easier. So we need two numbers that multiply to give us 8 and add to give us 6. And again, this is going to be 0. If this is 0 or this is 0, x equal minus 4 is going to make this 0. X equal minus 2 is going to make that 0. So these are the fixed points. If we did it right, we don't have to check. Let's check these. So let's check, put them back in the original function. So if you put minus 4 into the original function here, we're going to have minus 4 squared plus 7 times minus 4 plus 8. That's going to give us 16 minus 28 plus 8. So it's going to be plus 24 minus 28 gives us a minus 4. So that looks correct. And let's check the other one. Usually we won't do this, but let's just verify this. Put this in 4 minus 14 plus 8 is minus 2. So those were correct. We calculated, found x equal minus 4, x equal minus 2 were fixed points, and we checked them. Put in minus 4, get minus 4 out. Put in minus 2, get minus 2 out. Let's try this next function. H of x equals sine of x plus x. And let's set the range here from, let me set x to be from 0 to 2 pi, so that we don't have an infinite number of answers. So again, solution. Once again, set our function up here. Sine of x plus x equal to x. So that's the first step, because we want to find the place where our function, we put in an x and we get out an x. And then this is going to be sine of x is 0. And of course, the things that are going to solve this are going to be what? X equals 0, x equal pi, x equal 2 pi. That's why I limited this here, because we'd have an infinite number of solutions if we didn't limit this. So let's do one more. Let's take a look at this one here. Find the fixed point of fx equal 4x cubed, like this. Once again, set our function 4x cubed equal to x. And then once again, rearrange this. Now, probably remember, we can't divide by x because we don't know that x is not going to be 0. Remember, you're only allowed to divide by x in a function if you know that it's not 0. So we're going to have to rearrange this a little bit. make this 4x cubed minus x equals 0. But we can factor this, can't we? Factor out an x. This will give us 4x squared minus 1 is 0. And what's going to make this 0? Obviously, x equals 0 is one solution. And then also, whatever makes this 0 will be another solution. And set this. And 4x squared equal 1. X squared equal 1 over 4. Then take the square root. Remember, when we take a square root, we get a positive and a negative. So x is going to be the square root of 1 over 4. And x is going to be the negative of the square root of 1 over 4. And of course, the square root of 4 is 2. So we have these solutions up here. X equals 0. One over the square root of 4. And so these can actually be written. Let me write them all down. So fixed points are x equals 0, x equal 1 over s over 2. We take the square root. And x equal negative 1. So those are our fixed points. We take the square root here, we get 1/2, negative 1/2. So again, that's a simple way of finding the fixed point of a function. Just set your function equal to x. Now, the problem is that sometimes these are not easy to solve. In the case of these examples, we could solve these, we could factor them, etc., but that's not always going to be the case. Now, some functions are complicated, so the question is, are there times when we can be sure a function has a fixed point? So for example, sometimes we're not going to be able to find the fixed point by the methods that we have. So are there times when we can be sure that there is one? And again, this is something that can be very important in more advanced math, so we're going over it here. And there's a theorem that we have. And call this theorem 1. Suppose that a function f of x has these. F of x, in other words, the output is in the interval AB for all x in AB. So in other words, the function is such that when you put these input values from A to B, the output is also in the range A to B. Now, it doesn't mean that when you put in A, you get A out here, or you put in B, you get B out here. It doesn't mean that. It just means that if you're somewhere in the range A to B, your output will be in the range A to B. If you have that, and if you have 2, the function is continuous. Is continuous on A to B. And so then, if these are both true, then f of x has a fixed point on the interval AB. So let's get a general idea what this might mean. Let's look at this on a graph. Again, we don't know what the function is actually going to look like, but we know a couple things here. Let's take a look at this graphically. This is a general idea. That, again, we don't know what the specific function might be, but what this is saying is if you put in values of x between a and b, and the values of your function also fall within a and b, you will have a fixed point somewhere in this a to b interval, as long as your function is continuous. So what it might look like, you might have a function, who knows what it might look like. It could be something like this, or it could be maybe something, who knows, like this. But whatever it is, this theorem says, again, if your input is between A and B, these could be any 2 points, on the x-axis, and the output of your function is between those same 2 points, then you will have a fixed point. Again, you can kind of figure any function that you can draw here that's continuous. If you were to try to draw a straight line through this, again, the y equal x line like I had before, it's always going to end up crossing your function. Again, as long as it's continuous. Of course, if the function not continuous, then you could easily jump over that straight line. So if you put this line y over y equal x here, it's going to intersect. Now, there's a way to prove this formally. I'm going to do that in a separate video because you may not be interested in that. But we want to use this theorem, though, in the future, because it'll tell us that we have a fixed point in certain cases. In addition to the theorem that we just looked at here, we have another theorem. So let's look at theorem 2. This is really a continuation of theorem 1. So let's say if in addition to the conditions of theorem 1, so we had those 2 conditions from theorem 1, we also have the derivative of the function exists on the interval AB, and 4, there exists a constant k between 0 and 1. Again, k is a constant, such that the derivative of our function is less than or equal to k, for all x in the interval AB. So again, this is in addition to the conditions from theorem 1, we have these two conditions, that the derivative exists on AB, and then exists a constant such that the derivative of our function is less than that k on the interval AB, then the fixed point on AB is unique. So again, if we have these four conditions, the two we had a minute ago, that the input is on an interval AB and the output is on that same interval, and our function's continuous on AB, we have a fixed point, but also the fixed point is unique if we have these two extra conditions, that the derivative exists, and then the derivative is bounded by some number between 0 and 1. And now we can find this function, this fixed point, we can find this fixed point. So theorem 1 and 2 are important to tell us that we have a fixed point in certain cases. And then in other cases, we don't only have one, but it's going to be unique. Again, if we have these conditions. And I'll prove that theorem in a separate video. It's probably not necessary for you to know that. Probably depending on what you're doing, you may not be interested in the proof. So I'll just kind of do some applications. So let's actually take a look at this problem here. And this is from the textbook by Burden and Fairs. Use the last theorem. And I should say last theorems 1 and 2. To prove that g of x equal pi plus 0.5 sine over x over 2 has a unique solution on the interval 0 to 2 pi. So let's take a look at this. So let's see what we have here. So we have this interval 0 to 2 pi, and we want to show, to be able to use our theorem, we want to show that the output is also going to be between 0 and 2 pi. So let me write that down. So the values of x are 0 to 2 pi. So we need to show that g of x is on that same interval 0 to 2 pi. Or, another way to write this is just simply to say that g of x is between 0 and 2 pi. So let's take a look at this. So consider our function. And let's look at what we have up here. So up here, consider sine over 2 like this. So the question is, what values does the sine take on? For no matter what you put in. Now we could look specifically at this and try to figure out, what values it's going to be, but we may not have to get so specific. We can just say, okay, what the values of sine, that the sine of anything, no matter what you put in, the output is always going to be between -1 and 1. You could, again, narrow that down more. We may not need to. We know that this is true. And then also notice up here, we're multiplying it by 0.5. So we can also say if we multiply 0.5 across here, also, we can say that if we multiply by 0.5, multiply this by 0.5, this all the way across. So 0.5 sine of x over 2 is going to be between -0.5 and 0.5. Now let's put our whole function together. Now let's add pi to that. So add pi. Let's do that. So what I did here, I just added pi all the way across so that we would get our function up here. So we can see now that our function is going to always be between pi minus 0.5 and pi plus 0.5. And of course, now when we do this, this is going to be greater than 0 because pi is like 3.14. So that's going to be greater than 0. That's going to fall somewhere in here. And of course, pi plus 0.5 is going to be less than 2 pi. So we can say based on this, that this is greater than 0. We can say this is greater than 0 because that's greater than 0. And this is less than 2 pi. That we can say that. And of course, this is our function. So g of x is in the interval 0 to 2 pi. Again, there are other ways that you could have constructed this. Again, you didn't need to go through all these steps. You could just kind of look up here and say, okay, this is always going to be between -1 and 1. And therefore, this will be 0.5 times -1 and 1. So you'll have -0.5 plus pi, +0.5 plus pi. And that's going to fall in this range 0 to 2 pi. So you don't have to go through all these stuff, but it's kind of a rigorous way to say it. So we have this, and also our function's continuous, right? Because if we're putting values of x 0 to 2 pi, this sign is going to be continuous. Pi is just a constant. Of course, that's continuous. Also, g of x is continuous on our interval, and actually it's going to be continuous really for any real numbers. Therefore, by theorem 1, g of x has a fixed point on the interval 0 to 2 pi. Next, we want to show that our fixed point is unique. And so we need to find the derivative and show that the derivative is bounded by some constant between 0 and 1. So again, let's go back to our function. And first of all, the derivative does exist because the derivative of a sign exists, but let's actually go find it. So let me just write down our function. G of x is pi plus 0.5 sine x over 2, and take the derivative of this. And again, remember, derivative of pi is going to be 0 because pi is just a constant. And then, so over here, we're going to have to use the chain rule, aren't we? So this is going to be, the chain rule will be 0.5 cos x over 2 times the derivative of what's here. That's going to be 1/2. And actually, when we put 1/2 and 0.5 together, that's going to be what, 0.25 or 1/4. I don't know how you'd like to write. Let me write it 0.25 cos x over 2. And the question is this going to be, is the absolute value of this going to be bounded? So what's going to be the absolute value? Is once again, cosine varies between -1 and 1. And also, therefore, if we multiply by 0.25, we can say that 0.25 cos x over 2 has to vary between 0.25 and 0.25. Again, and remember, this is the derivative. This is our g of x, g prime of x. If a function varies between a positive number and the same negative number, then we can say that the absolute value of that function is less than the constant, like this. And of course, this is less than 1, between 0 and 1. So g of x has a unique fixed point on the interval 0 to 2 pi, because we were able to show that this derivative is going to be bounded by 0.25. At least the absolute value of it is bound by 0.25. And according to our theorem, that number, since it's greater than 0 and less than 1, it bounds our derivative Therefore, we have a fixed point on that interval. As I mentioned, sometimes it's going to be difficult to find fixed point just by solving explicitly an equation. And so now the theorems, they told us, okay, when we might have a fixed point. And so the question is, how do we solve these iteratively? How to find a fixed point So how do we find the fixed point iteratively? And let's do this. So suppose we wish find a fixed point of a function. You can call it f of x. Then what we do is set x equal to fx like we normally do, except I just rewrote it. Before we were writing f of x equal to x, I just reversed it. It'll be a little bit more convenient this way. So we can find by using iterative method. And again, if you're familiar with the iterative method, let's say we have x of n plus 1, f x n like this. And what we'll do, we'll guess it like, say, an original starting point. I don't know what you want to call it. Maybe guess it like maybe x naught. And then solve for x1. And then go through the process again. And let me actually just be a little bit easier to do this in an example. So let's say we have this example here, and this may take quite a few steps, but find fixed point for f of x, 6x squared plus 3 to the 1/3 like this. And so again, first of all, let's just guess. Maybe your x naught is equal to 2. So again, what we're going to do then is like we have up here, we're going to have like an x1 equal fx naught. So we'll put 2 into our function. 2 into the function up here. The 1/3 power. And when you solve for this is going to be 3. And so that's going to be our new guess. This is the new guess. And so when we do the next one, we're going to put this 3 into our function. We put this just into our function and find another guess. So this is going to give us 3.8485. Then that's going to be our new guess. Put this into our function. And when you calculate this one, you get 4.512. So that's going to be our new guess. This calculate, and now it's going to be our new guess. Calculate this. Now it looks like it's finally starting to converge a little bit. And that's going to be our next guess. And plug that in. This, and actually, it's going to take quite a few more steps, but it looks like I was getting it to converge down to about 6.0632. In other words, we're going to stop when we start repeating these numbers. Like, for example, let me put the one just before that. So, in other words, I did it several more times, and I got 6.054. So now notice there's very little difference between that and the next one. So when I put in 6.054, I got out 6.0632. So it looks like we're converging close to the fixed point. So again, the fixed point is going to be there whenever two consecutive numbers are very, very close, or they're actually going to be the same. And so by doing this method, you'll eventually converge on a fixed point. Sometimes it may take a long time, or sometimes if your guess was way, way off, maybe it won't converge at all. But this is kind of the way you do it iteratively. Now, obviously, this is best done on a computer doing just a simple algorithm to calculate a fixed point. In that case, that's how you would find a fixed point iteratively. You'd make a guess, put it in. Now, if the first try you got the same thing out as you put in, if you put 2 in and had gotten 2 out, then you just stop. But if not, you'll put that value in the function, see what you get, put that value in, see what you get, that value in, see what you get. In this case, my guess looks like it's pretty far off because it's taking a while. Then finally, when I did this several more times that I didn't show here, but finally up here, I got to like 6.05 and 6.06. You can see it's converging. And so the fixed point is going to be somewhere in there. And again, if you want to get it exact, you have to go a few more steps. Like I say, this really should be done on a computer.